Okay, hello everyone. Welcome to the lecture number 14. Uh, so previously we started to talk about, well, we went pretty far with that, about the dynamics of the thermalization, right? So the setup was that we imagine we have a system S that is coupled to its environment in the form of thermal bath at some temperature beta. And we wanted to deploy our methods of open system theory to analyze, to observe the process of thermalization. That is when the initial state of the system S over time goes to the thermal equilibrium with the temperature same as the temperature of the bath, hopefully, right? And I guess our analysis, the things we get to can be summarized by this formula here. Let me highlight it a bit. So we can summarize it with this formula, which essentially demonstrates the process in a sense. Okay, it's not full description yet, but it's almost there. So let me break it down to you just to remind you what we were doing last week. So we have here some arbitrary initial state of our system S, which is open to bath again, and we are acting on it with this dynamical map M. Just as a reminder, what is this M? So we worked in the so we assumed that the coupling between bath and our system is weak. So we had weak coupling regime here. So that we could deploy Born-Markov approximations, which is also justified by the long time scales we are interested in here, because we want to see the asymptotic where our state ends up in, right, when time goes to infinity. So all the Born-Markov and secular approximations are justified then. So we are working. So our dynamics is generated by Davis generator, L Davis. L Davis, right? Which has a GKLS form, which we described previously and the lectures before that. But one of the things we fairly early on identified about our system, that if the Hamiltonian of system S, well, this is this effective Hamiltonian that's corrected by the average coupling, right? If it's not non-degenerate, so energy levels, each energy level is unique, has a unique value, then the Davis generator becomes block diagonal. And this is where M comes into. So if I write it as a matrix, so this is this M. Okay, this is M. I, J plus G matrix. Let me write it like this. Zeros here, block diagonal. That's what block diagonal means. And those blocks, this one is spanned by projectors. So I call this BP. So this is basically a subspace spanned by operators, basis operators of this form. So these are projectors. So these are projectors onto eigenstates of system Hamiltonian, okay, projectors. And the other block is spanned by what is remaining. So I call this BC because it's a subspace spanned by coherences. A not equal to B, okay? So when we found out that this block, this matrix M, this M here, is symmetric, is Hermitian with respect to this modified inner product. which means if it's symmetric, it means that it has real eigenvalues and a full set of orthogonal eigenvectors or eigenoperators in this case, so which we call them Q, right? Which means that you can take any initial condition, like any density matrix, decompose it into bases made out of eigenvectors of this superoperator M. And once you do it, you write it as this kind of superpositions combination. The evolution is very simple. You just multiply it by E2 minus E2, sorry, eigenvalue times T. Okay, so this is the origin of this whole formula here. And things to note that we found out that there is always M always has one eigenvalue 0, okay, which corresponds to the steady state solution for this master equation, for this map. And the steady state solution is the same as the equilibrium state for our system, okay, which I denote here P as beta, and it's proportional to E to minus beta HS. Okay, and we know that there is only one from H theorem, which we talked about previously, and it's zero eigenvalue. That is why there is no exponent here, right? Something like this, because it will be E2 power 0 times t. Okay, so nothing changes, and the properties of this steady state eigenvector for M are such that when you do the projection like this, it boils down to taking a trace of the argument. Okay, that's why the trace is here. So other eigenoperators are not cannot be interpreted as density matrices because they are traceless. This density matrix has to be trace 1, right? Positive operator with trace 1. Those are not those. Qs cannot be interpreted like that. But they still form a basis, so we can decompose any density matrix into this basis. So one eigenvalue is 0, the one corresponding to the steady state solution, corresponding to the thermal equilibrium. All the other eigenvalues are negative, strictly negative, which means that's why we wrote it like this. And it means that any part of the initial state that's not parallel to the thermal equilibrium state, okay, gets erased by this kind of exponential decay, okay, with eigenvalues setting the time scale on which this decay happens, right? But when t goes to infinity, we can be assured that all this will disappear and only this bit will remain, which means we observe almost observe thermalization, because again, this is what happens on the block on the subspace spanned by projectors. Okay, and this is almost all that we need, because thermal equilibrium is actually diagonal. I mean, thermal equilibrium state. Where is my cursor? Right, it is spanned by minus beta energy as a, right, it is proportional to, because there is also normalization, right? But it is spanned by projectors, right? So this is like, if this thing failed to generate, if M failed to generate for us equilibrium state, we would be cooked. Okay, there would be no possibility for thermalization. So So this is what we arrived at last week. But this is not the end of, not the complete end of the story, because, like I said, we kind of solved the problem inside this block, okay? But to get full thermalization, you also have to take care of the other subspace, okay, spanned by coherences. And in particular, you want to take any initial state that has some pieces has some pieces on diagonal and some pieces on off diagonal, right? And you want the diagonal to converge to equilibrium state, and what's on the off diagonal, you want to get rid of it completely. In other words, if I take my initial density matrix and just throw away the diagonal part, because this is what the above equation is taken care of. So we are just focusing on the stuff that's spanned by coherences, as you can see in this sum, and we act on it with our Davis map, right? So this will reduce to this block acting on our coherences. And what we want to see, what we would like to show that is happening, is that as time goes to infinity, this goes to zero for every coherence like that. Okay, then we are sure that any initial state becomes diagonal, and the stuff on the diagonal converges to equilibrium distribution. That would be a full proper thermalization as we defined it in the beginning of the previous lecture. And there are some things to note about this, because of course, there are some complications here. Uh, uh, so one complication number one is that if you look at the matrix elements of diagonal matrix elements of the initial density matrix, or of the density matrix time t, as I wrote it here, these guys, they are complex numbers in general. Okay, so this cannot be interpreted as probability distributions, right? Which is kind of unfortunate for us, because we cannot use, for example, H theorem that we employed previously to show this effect of thermal state being an attractor, right? But it's okay, it's fine. Let's say we don't have this good very informative theorem to rely on, but we still could try to do this kind of eigen system analysis, right? To look at the dynamics and maybe witness that there are only negative eigenvalues or something like that, right? And then we will be sure that nothing will be left after time goes to infinity. But there is another complication here. So you see, I wrote here this generator in this block. It has like two pieces: G, dissipative part, let's say, and I times J. This is like the Hamiltonian-like part, the stuff that typically it's called lamp shift, because this is, you look at it and this is something that, let me write it a bit. What is meant by this? So Ij is something that can be written as I don't remember if I used minus here. It is a commutator with let me call it, let me write it like this, okay? Where this, so this is like a commutator with an Hermitian operator inside, okay? So this looks like a term that you would get from just mm, mm, unitary dynamics generated by a system Hamiltonian would also have this form. So you can look at it and see it as like, oh, this is like another correction to the original Hamiltonian of the system, right? The lamp shift, because it shifts energies around. Uh, and so that's why, and the other guy, G, is not of this form, okay? It's definitely not just a shift of energies. It has all the all the decoherence stuff is encoded in it. So you have those two parts, right? And now you can check that both the G part, the dissipative part, so the explicit form of let's say, of matrix of this operator that we would like to use to, check that it's Hermitian, as I wrote here. You can grab them, infer them from the assignment 34. We went through on the previous lecture, and I don't want. You know what? Maybe I will write down it a bit, because if you go to equation 322 in the script, there is the full calculation showing that how G looks like, matrix elements wise, and the proof that it is Hermitian, like it's written here. But let me write down how G looks like, just for you to have some idea what we are working here. So G is it works in this subspace spanned by coherences. So like the elements of the basis elements spanning the subspace, it's have this form. So you need like two indices to index both, input and output. That's why I will write G as a pair of index pairs. Okay. So it's like CD AB, which what it actually is you take the output basis operator. You have to take dagger because we're using here this trace inner product, and you take G super operator acting on AB. Okay, so this is what this formula encodes, and you can actually calculate this guy using the things we derived in solution to assignment 34. And the formula I get is not super complicated, but it's kind of lengthy. So there are some cute stuff. You have a lot of deltas here, okay, which is always useful. So you have two deltas, so right, it means that C, A have to be the same, and A and DB has to be the same, okay? So that simplifies things a lot, in this term at least. But the coefficient is a sum over indices F, and you have here a combination transition rates at frequency omega Fc, and then matrix elements with the coupling FCT plus omega FD. And it's always transition rate always comes with the corresponding modulus square of coupling operator. So that's one part, but there is another part here, minus delta, also delta, but this delta just makes sure that the energy is conserved, AB. So omegas are the same, W, E, the rate, omega CA, S, CA, complex conjugate, S, D, B. So this is how it looks like, okay? And now you take it and you want to check what happens when you flip G from acting on B under this inner product to A, and you find out using the detailed balance, the symmetry of transition rates that we used a lot on the previous lecture. So let me remind you, detailed balance. So this is a special symmetry of transition rates. So you take a ratio of a transition rate to, omega. So if I write down some energy levels, HSA, HSP, whatever, you have ladder of energy levels. Omegas are the differences between those energy levels. So for example, omega AB would be HSA minus HSB. Okay, so this transition rate omega, you can think of it. Let's say omega is positive. This frequency is positive, so you can think of it as a transition rate of going from one level, let's say this one, to this one. So this would be if omega was set to omega EB, right? And let me change the color. So W of minus omega is like a opposite process. So if this is omega EB, then minus omega is omega BA. Okay, so this would describe a transition going back, right? And when you take a ratio of those two guys, there is a special rule that applies here, because this ratio is fixed by the temperature of the bath. Okay, it's this very special form. So this is detailed balance, quite an important thing, and it because it basically appears in every piece of our generator of evolution, right? This detailed balance implies a lot of special symmetries for the for J, G, and M, and all the other pieces of the generator. So when you use those symmetries, you can quite easily show that. If you want to see details, go to equation 322. I won't be writing it down here, but you can show that G is Hermitian. So okay, it's Hermitian, so it means that it has full set of, it has real eigenvalues and a full set of eigen operators, eigenvectors that can be used as a basis in this subspace spanned by coherences. And on the other hand, you can do the similar calculations for the other piece, J, and you can show that it's not Hermitian, it's anti-Hermitian. It's anti-Hermitian because there's I here, so J itself is Hermitian, but it's multiplied by I, so it flips sign. That's why it's anti-Hermitian. But being Hermitian and anti-Hermitian is just it's not very important, because anti-Hermitian operators, superoperators, also have real eigenvalues and full set of orthogonal eigenvectors or eigenoperators, which can be used as a basis, okay, for spanning the subspace where J operates. So this one have eigen basis, this one have eigen basis. So it seems that everything is fine and good. However, the generator is the sum of those two guys, and they don't commute, which means that the one you cannot use basis of one to diagonalize the other in other way around. Okay, you have even though we know we can find basis for J and G independently, for the sum we don't have that. Okay, we cannot use this. And to make matters worse, since G is Hermitian and J is anti-Hermitian, IJ is anti-Hermitian, their sum is neither of those, which is which is troublesome because it means that there is no guarantee. I mean, you still have eigenvalues, although now the sum can have complex value eigenvalues, okay, which is a one complication. But the more pressing complication is that you have no guarantee anymore that you have a full set of eigenvectors for the sum that could be used as a basis. Uh, and if you don't have that, you don't have a guarantee that you can do this kind of decomposition. Okay? At least not not in the sense that you make a decomposition in terms of uh, eigenvectors. But all is not lost because even if you are in such a situation as this, there is still a lot you can learn. Okay, so let me get into it a little bit. Uh, so still, even if your generator is not Hermitian and anti-Hermitian like in our case, okay? Uh, it's still a linear operator. It still has eigenvalues. Okay, this is just a fundamental feature of algebra that any linear operator you can always look for eigenvalues of linear operator because the theorems tell us that okay, so we have our linear operators or super operator ij plus g. Okay, and the linear algebra tells us that if you calculate the following thing, the determinant of the matrix ij plus g minus coefficient mu times identity, which let me write it like this, that it is a super operator and then identity in a subspace spanned by coherences, because we don't have to, this is where we operate in. So you take this matrix of this, subtract identity times coefficient, and you take determinant of this matrix. And this is something that's called characteristic polynomial. Polynomial, okay. It's a polynomial in this coefficient mu here, this variable mu, okay? And the algebra, the mathematical theorems tells us that when you equate it to zero, okay, the roots, so the solutions of this equation, mu that solve this equation, this is what gives us eigenvalues of this super operator, okay? And the fundamental theorems tells us that this equation always have as many solutions as a degree of this polynomial, which is equal to the dimension of our matrix, okay? So in other words, what this means that you can take determinant, this characteristic polynomial, minus mu times identity BC, and you can write it in the following way. Product of factors of this form, fk minus mu, right? So you have a polynomial. You can write the polynomial as a product of how do you call this? I think it's like a canonical form or something like that, right? You have polynomial. If you know its roots, you can always write it in this form where mu k are the solutions of this equation. Okay, so the roots of the polynomial, and those mu k's are the eigenvalues of this matrix. Okay. However, it's some of the eigenvalues can be the same, right? So in other words, this whole product can be further simplified into this kind of form, and 2, and so on. And the power here, which is it's called the degree of degeneracy. So if the power and 1 is not 1, not exactly 1, that means that you have this you have a number of eigenvalues that have equal value, okay, and then you say that your this eigenvalue is degenerate, okay, because there are multiple eigenvalues that are the same, and this power here is called the degree of degeneracy. Okay, so this is degree of degeneracy. It's a scary name, but what can you do? This is what degree of degeneracy. So if nk, some nk is greater than 1, nk is greater than 1, we say that eigenvalue mu k is degenerate. Again, degenerate. Okay, so that's the nomenclature, which you probably very well know. And now the issue comes up. So if you now, let's imagine we have a degenerate eigenvalue for our superoperator here. And now the issue comes up with what are the eigenvectors corresponding to those degenerate eigenvalues, okay, to this block of eigenvalues. And the issues may come up that the number of linearly independent eigenvectors of this degenerate eigenvalue might be smaller than the how do I phrase it? Oh yeah. So it may happen that the number of linearly independent eigenvectors corresponding to the degenerate eigenvalue is smaller than the degree of degeneracy. Okay, so let's say you have a eigenvalue mu1 has a degree 3, but you have only 2 linearly independent eigenvectors corresponding to those 3 eigenvalues. Okay. If this is in case of Hermitian matrices or symmetric matrices in general, or normal matrices in general, the number of independent eigenvectors always have to match the degree of degeneracy. Okay, so there is never a question if there are not enough, if there is a mismatch there. Hermicity guarantees that it's always the numbers always match up. But in general, it doesn't have to work like that. And if there is this mismatch, this means that you don't have enough linear independent eigenvectors to form a basis for the whole space, okay? Because you are missing some of them. And if this is the case, then you don't have the basis. You cannot do this very nice eigenvalue decomposition for the dynamical map, right? So if this is if this is the case, if your number of eigenvectors doesn't match the degree of degeneracy of the corresponding eigenvalue, you call matrix defective. Defective matrix. Defective matrix is when the nk the number of linearly independent eigenvectors is smaller than the degree of degeneracy. Of the corresponding eigenvalue. Okay, so those are defective matrices. To give you a simple example, and the simplest example. So in matrix, let me call it A. So in text, in the document, I use a notation for matrix, a boldface capital letter. Of course, it's quite difficult to do it on the to do boldface on the on handwriting. So I will do double bar. So vector is like one arrow. So this is kind of matrix is like two arrows, but it would look awkward. So just two bars. So this is a boldface. Think of this as a boldface. So let's take matrix A, which is 2 by 2, have some coefficient A on diagonal, 0 here and 1 here. Seems very simple, but it turns out this is a defective matrix, which you can easily show. So to find the eigenvalues, we have to solve the characteristic polynomial. So we take determinant A minus mu 1. So I then, the matrix that can say ones on the diagonal and 0 everywhere else. And you take determinant of that guy. So determinant of matrix of this form minus mu 1, 0, A minus mu. Determinant of 2 by 2 matrix is quite easy to calculate. And you get that is I minus mu square, which is it's cool because it already has we don't have to solve we don't have to find the roots because we already offer this canonical form. So the roots, it's very easy to find the roots of this polynomial. They are equal A. Okay, so we have degree of degeneracy 2. So we have a eigenvalue mu1 equal to A with degree of degeneracy and 1 equal to. Okay, so we have two eigenvalues, as you have to have in case of 2 by 2 matrix, but they are degenerated. So far nothing is amiss, but now let's look for eigenvectors. So this is standard approach to that. You have to solve the following coupled equation. So you're looking a zero vector on left hand side, and on the right hand side you take your matrix A minus you pick the eigenvalue, so A in this case minus identity, and act with it on the on some vector R1, R2. So R1, R2 are our unknowns. If we can solve this equation for R1 and R2, this is what gives us the eigenvector corresponding to eigenvalue A. Okay, and this is not very difficult to find. So this would be R vector of A. So eigenvector corresponding to eigenvalue A. And you can just we can just calculate this stuff. So our matrix, it has ones and a's on diagonal. If you subtract a from the diagonal, you get everywhere zero except for this upper corner. Acting on one or two. Well, that's fairly simple. What you get is R2 0. Okay. It might worry you a bit because the only thing you can the thing you get from this that R vector A is 1 0. Okay. From this equation you get that R2 has to be 0, right? And R1 is whatever, so we can pick R1 so that it's the whole eigenvector is normalized. So we pick 1. But here is the issue because there is only one solution to this equation, right? So there's only one eigenvector, two eigenvalues, and we have two-dimensional space here. This is just not enough to form the basis, right? So this is the illustration of defective matrix, not enough eigenvectors to form linearly independent set that could be used as a basis for the space. Not enough to form basis, yes. Okay, so this is the issue that we can run into with J plus G. Okay, we wouldn't run into this issue if we just looked at J alone or G alone, but the sum, as I explained, is not Hermitian or anti-Hermitian, so they can be defective. Okay, so what to do with defective matrices, or the option of defective matrices, if we want to do our eigen system analysis to uncover how the dynamics actually works. Uh, Excuse me, the message. So where am I? Okay, so let's do some cogitating here. So if we have a matrix B, and let's say this is non-defective. So we don't have an issue with not enough eigenvectors. So if it is non-defective, if we have enough eigenvectors to form the basis, we can always diagonalize the matrix. What I mean by that is you can take the result. You can always find a transformation S such that you can take your matrix, and sandwich it into S minus 1 and S to transform this matrix to have a diagonal form. And a diagonal form means that you have eigenvalues on the diagonal. So let's write it like this. And 0 everywhere else. Okay? So this would be eigenvalues. And in this example, we have a lambda 2. We have two identical eigenvalues. So in this example, B has a eigenvalue that's degenerated with degree of degeneracy 2, for example, right? And now, why this is important that you can diagonalize non-defective matrices? Well, because you can use this knowledge about eigenvectors and the deformed basis to calculate the functions of B, like for example, dynamical map. So in case of exponent, right, this is a very well-known result. If you have something like this, right, you can you can write it in terms of like a function. You can write in terms of Taylor expansion, right? So you write it like tk over k factorial, and you take b to the power k. But now b to the power k, you can easily write it by s minus 1 times s equals s times s minus 1 equals 1, right? You can always multiply it with 1 in between every b here. You can insert identity, and identity you can split in those two using those two relations, right? And if you do that, you can transform everything into the following form: k from 0 to infinity, tk k factorial, s minus 1b, s to the power k, s minus 1. You can write it like that. So you just get s e how do I want to write it? E to power t and the diagonal form of a matrix, right? Because s minus 1 bs, it's diagonal, s minus 1. And and it is very easy to calculate the function of diagonal matrix. It's just s acting on et lambda 1, et lambda 2, and so on, right? Super easy. And this is nothing else what I'm doing here than this is the formula I just wrote is corresponding to this decomposition we did here, essentially, okay? Those factors here, attenuation factors, are corresponding to those factors on the diagonal, okay? And now if your matrix is defective, so let's take C that is defective, we cannot do diagonalization, not enough eigenvectors, but we still have eigenvalues, and we still would love to be able to calculate functions of this matrix, for example, exponent specifically of this matrix. We have a use case for this kind of thing. We want to calculate exponent of this guy here. So as it turns out, there is a way of finding this kind of transformation that it won't diagonalize your matrix C, but it will bring it as close as possible to this very easy diagonal form with which you can calculate a lot of functions. Okay, you can calculate a lot of functions when you do this transformation. This is called the algorithm you are looking for is something that finds generalized eigenvectors. Okay, this is the keyword here. So if you have you have some number of eigenvectors available to for your defective matrix. Okay, you can find them. Let's say they will be they are linearly independent between them, so you can orthogonalize them and so on and so forth. So if you want to form bases using those eigenvectors, right? You have to have some some motivation, uh, what how to fill in the gaps, the missing elements for your bases, right? And the need to if your motivation is to be able to quite easily calculate functions of your matrix C, or in other words, to transform to find such a basis, to construct such a basis in which the matrix of your defective matrix will be as close as possible to this diagonal form, so that you can easily calculate the functions. So if you have motivations like that, you can start looking for some algorithm for filling in the gaps in your set of eigenvectors, right? And there is one such algorithm. This is where generalized eigenvectors comes in. And the idea is that once you follow, I won't go into details about this algorithm. I have to admit, I don't, I haven't bothered to learn it, but you can look up Wikipedia, for example, to see what you have to do if you are actually if you are in need of finding explicit form of generalized eigenvectors. But the idea is that you can fill your bases in such a way that you will be able to find a transformation N that when you act, you sandwich it, you sandwich C, your defective matrix with it, you will bring your matrix to the following form. So there are stuff going on diagonal. Let me highlight a block. So you have blocks on the diagonal such that on the diagonal you have eigenvalues, the degenerate eigenvalue. Okay. Maybe let's make the block a little bit bigger. Let me make the block a little bit bigger so that I have 4 at least. So that would correspond to the degeneracy degree of degeneracy 4. So you have on diagonal, you have eigenvalue, okay? And then on super diagonal, so one band above diagonal, you have ones. So one here, one here, one here, 0, 0, 0, and 0 here. And you can have, if you have more degenerate defective eigenvalues, you will have more blocks like that and zeros everywhere. Okay, so this thing is called the Jordan block. Jordan block. And this is a Jordan form. Okay, this N you fill in, you find, and because this N executes the transformations from your original basis to the basis made out of eigenvectors plus the generalized eigenvectors you found out using the algorithm. And this transformation brings you to the Jordan form of the matrix. And this is a Jordan form for this A matrix, okay? This simple 2x2 matrix. This is the Jordan form for any 2x2 defective matrix, okay? So this is basically a generalization, a higher dimensional generalization of this our example here. So this is something you can do. Okay, you can execute this procedure, this algorithm, and what once you have this, you can calculate you can actually calculate the exponent. Well, many other functions also, but exponent is what we are interested in specifically. So you have ETC, right? C defective. So you do the same trick as previously. So you know you have the sandwich ET n minus 1 CN, right? And minus 1. So you have your sandwiching exponent T of this Jordan form mu1, 0, mu1, mu, right? So this Jordan form n to minus 1. And as it turns out, if you do the math, this thing actually can be like calculated explicitly. X is good in that way. So let me write it like that. So let's focus on this block here. I use here 3, degeneracy of level 3. Okay. So what you will get if you do the exponent. So here is the corner of the Jordan block. So you will get E mu T. Okay. Then this 1 here, what it will cause when you start taking higher and higher powers of this matrix. So this will give you T times E mu T. And then you will get 1 over 2 factorial, T square, E mu T, so on, 0, E mu T. Hopefully you can see the pattern, what's going on here. 0, 0, E mu T. I actually took here a block, the degeneracy, degree of degeneracy 3, so it should actually cut off here. The block would be 3 by 3 and would cut off it. If it was larger, you can see the pattern. You would get here 1 over 3 factorial T to the power 3 E mu T and so on. And that's basically what we actually need. So you have this transformation n. So this is what you can use to do the decomposition, generalized version of this decomposition. Okay, you take your initial density matrix, you decompose it using this basis filled in with generalized eigenvectors. And once you're sitting in this basis, it's easy to calculate I mean, it's much easier to calculate how the exponent, how the map works. And the thing to observe here that there is some complications, not just add e to the power eigenvalue times t. You have those other terms that will mix the different terms of the decomposition, but they have the form of like polynomial, but still times e to power mu t. Okay, so this whole Jordan block, it still decays as mu, or decays. Well, if mu is negative, it decays. If it's not, then it blows up. But it's still like this e to power mu t, right? You have this attenuation factor here. So to summarize this, uh, even though our generator in the block span by coherences is might be defective, right? So we don't have this easy eigen system decomposition that works so well on the diagonal to give us this first part of thermalization. Uh, Still, we are not completely lost because we can still perform this generalized diagonalization, this Jordan block stuff, and from that we know that the behavior of the map generated by ij plus g is still have this still will have this form of some combination of terms that are attenuated by these exponential factors. So if we know eigenvalues of our generator, if we know eigenvalues of this guy, and we can show that all those eigenvalues, they can be complex values, so that all the real part of each of those eigenvalues is strictly negative, okay, then we know that whatever this map will act on will decay exponentially to zero, which is what we are looking for, right? So we cannot allow to get a full proper thermalization, to get the full dephasing, well, stuff on the off diagonal of the density matrix goes away. We need to show that eigenvalues of ij plus g are strictly negative, or a real part, at least real part of those eigenvalues are strictly negative. If some of them are zero, then it's not good because it would mean that you will have some pieces on the diagonal of the density matrix that don't decay, they just oscillate or something like that. So you don't have full proper thermalization then. So to get a full thermalization, we have to check that real part of eigenvalues of this sum is strictly negative. Okay? Uh, so one way to do that would be to solve the characteristic polynomial, which of course it's kind of difficult. It's almost never possible to do, but there are ways around it. There are other ways that we can do. For example, we can check uh, we can check, we want real part of the eigenvalue to be strictly negative. So it would be enough, it would be sufficient for us to show that G, the Hermitian part of the generator, is a negative definite. This is a negative matrix. Oh, negative matrix. Okay. So let me be more precise about that. So showing that the matrix is negative, uh, G is negative when for every operator A, G, A, you pick your inner product. We have our special inner product in a bag, okay, and you take like a average value of your operator G, and it's negative if it's for every non-zero operator A, this is negative, okay? This is what it means that you show that operator is negative. If if you show that this is greater than zero, you would show that it's positive. It's greater equal zero, you would show that it's positive semi-definite. Uh, Smaller equal to zero would be negative semi-definite. But we don't want it to be semi-definite because we want to be sure that all eigenvalues, the real parts of eigenvalues are strictly negative, right? So that we have our exponential decays everywhere. And why am I talking? We need to show eigenvalues of the full ij plus g to be real part to be negative. So why am I talking about g? Well, say we are able to show this, then a special case if you can select for a uh, one of the eigenvectors of ij plus g. So let me write it like this. Mm, So mu times r mu r mu s beta. So that would be eigenvector of ij plus g. Let's say we found one, okay? And we just write this down. So if we normalize r, that would be just one, right? And you multiply it by the corresponding eigenvalue, which we can write as real part of mu plus I times imaginary part of mu. And still the same thing here. I'm building up to something here. Okay, don't worry. There is a plan here. But eigenvalue. So we can write it as r mu as pull in the number here. I in mu r mu. I just pulled in the eigenvalue inside the inner product. But if this is the eigenvector of ij plus g, so this means that this is just equal to r mu ij plus g acting on r mu, right? This is what it means that is eigenvector, right? The operator acts on this eigenvector, spits out eigenvector times eigenvalue, mu. But then we can do more about this. We can write it as I r mu j r mu as beta. So we just use the fact that inner product is linear, r mu g r mu. Okay, very simple. And now a couple of things. We know that J is Hermitian because IJ is anti-Hermitian. So this thing, this kind of inner product, the average value, any average value of superoperator J, be it this eigenvector R, be it any other operator A, this has to be real. So this thing is real. This is a real number, okay? Same with G. G is Hermitian. So this guy is also real. This is also a real number. Therefore, this thing here is purely imaginary. Purely imaginary. Because it's a real number times imaginary unit, right? So this is the imaginary part of the expression. This is a real part of the expression. But now, so this is just a norm of the eigenvector. So this is also real. Okay. So, and it's not zero. Real and different than zero in particular. Therefore, so this is real, this is purely imaginary. And on this hand side, we have a real part and imaginary part, right? Therefore, you get from here that the real part of eigenvalue mu equals R mu GR mu as beta. Well, in case we did not normalize the eigenvector, we just divided by the norm, right? In other words, the real part of eigenvalues is controlled by G. Okay. So now, if I can show this for any A, in particular, it will also work for R, and we would get then that this is strictly less than zero. That's why the issue of showing that we have a full dephasing, so the issue of showing that we have a full dephasing can be now boiled down to, thanks to our discussion about defective matrices and all that stuff, it can be boiled down to checking if the dissipative part of the generator in the spanned in the block of coherences is a strictly negative matrix. Okay? And now, fortunately, we can actually show that, but the calculations are even less inspired, is from what I understand about them, less inspired than what we were talking about so far. So I don't want to get into them because it will be just rewriting the stuff that's in the script. So if you want to see the details of this proof, okay, go to go to the phasing section in the script. So where is it? What number is it? I don't know. You go to section. Go to section 6.4, and the calculations start at page 72, equation 329. 329 onwards is the analysis that leads us to the conclusion that this is true for G. Although it's not always true, to make sure that it is true, we have to assume that SAB, so that's A, S, B, that these guys are non-zero for all A unequal B, okay? Well, also WE of omega AB has to be non-zero as well. Okay, so if some of those guys disappear, then you open up possibilities for getting zero eigenvalues and getting this weird oscillations of diagonal of the density matrix rather than exponential decays. So yeah, so I won't go into the details about the calculation. Check it out for yourself if you want to. Maybe there is a like a better, more robust way of showing this than what I did it myself. But if there is such a way, I haven't found it yet, or but maybe next edition, I will have some, better arguments than just straight up calculation. So yeah. So to summarize this, this journey of ours about dephasing, so we can finally say the following thing. We do have the phasing. So if we take, based on what we found out, if we take the map, the map acting in the coherence subspace, so J plus G. Yeah, let's take a matrix element of this guy, A, B, C, D. So we take a matrix element of this map acting on C row 0 S D. So one of the off diagonal elements of the off diagonal elements of the density matrix. Then, using the Jordan block form technique whenever it's necessary to be used. If it's not, you can just do normal diagonalization. But what we are getting is, we can always flip to the Jordan block form, and we'll get E minus T real part eigenvalue mu1 times I, because there's still, in general, there will be complex valued eigenvalues. So there's a imaginary part, possibility for imaginary part, and I will write it like this. So there will be a block matrix B1, which can depend on T. So this represents one of the first Jordan block, and you will get a E minus T real part of mu2, EI imaginary part mu2, times T, sorry, it should be T. And the next matrix that might represent block, Jordan block, if it's necessary. 0, 0, and so on for every eigenvalue. Flip back to the original basis. Matrix elements, CD 0, 0, S, D. And those guys B, change. It's a compact way of writing. So B, B of Ti. So think of it as so 1 T up to 1 over N1, the degree of degeneracy of eigenvalue mu I, Tn1, 1 T, so on, 1 T, so on, 1 until you reach the bottom corner. So this is a Jordan block. So this guy, this is supposed to represent this thing here. with the exponential attenuation factor extracted. So if your eigenvalue is defective and it has a degree of degeneracy ni, sorry, should be ni. It should be ni, not n1. Tni in the corner. Right, so if your eigenvalue happens to be defective with degree of degeneracy ni, your map takes this form, right? There is this block with some polynomial scaling inside it, right? But it's all multiplied by exponential decay because we know that the real part of eigenvalues has to be strictly negative. There are no zero eigenvalues here, no steady state solutions, which translates into, oh, and if your eigenvalue is not defective, then this B becomes just diagonal. So this is if mu I defective, if not, BIT is just one, just identity. Okay. So then simplifies, everything simplifies. But the conclusion stands that this has no choice but to go to zero as time goes to infinity because of those strictly negative, attenuation factors. Okay. Okay. So mm, let me take a minute of break before I close the thermalization bit. So let's take a couple of minutes of break. Okay, let's carry on with the business. So the last bit I want to talk about, it's a section 6.6, which may be a little bit too pompous, physics of thermalization. Okay, so we did a lot of math, maybe too much math previously, but now I want to like talk. Almost no math, just talking, just speaking now. So yeah, let's kind of like sum up what we learn and what we think about thermalization, how we imagine this process from the physics point of view, maybe not from intuitive point of view. Okay, so for me, the way I think of thermalization is I always think of it as something that's spreading. Okay, I it's very evocative for me to think of thermalization as some kind of disease. Okay, so let me draw some cartoons for you. So imagine that you have your patient zero, okay, the buff at temperature beta, right? It has a thermal state. It's initialized in the thermal state, right? Z E beta, right? So this is your patient zero, let's say. And now you bring in some unsuspecting healthy system S, okay, has its own Hamiltonian S0, right? It starts with some arbitrary state, initial state S0. It's going about its way, and now you couple them together, right? There is some coupling. comes in, right? L lambda S times F, right? Like in our model. And now the diseased system E, the buff, which displays its symptoms. Okay, bear with me with this analogy. Bears its symptoms in form of this thermal state, right? It starts to interact with S, and over time it infects it through the interaction. It infects it by, passing on the pathogen, whatever that is, and eventually S becomes sick as well, right? It starts to display symptoms, right? Over time, this goes to P as beta, right? It starts to display similar symptoms as the patient zero that started the infection, right? And now the way I envision it, that is once this happens, once this transmission is complete, the infection is complete, as it's kind of like assimilated into buff, or rather it becomes a vector for further spread of the disease. So if we brought here another system S prime, let's say, and we allow them to interact, rho S prime would also go to thermal equilibrium. Right? This is how I imagine it. Right? It's like a spreading disease, right? Start from the patient zero, something that displays symptoms. There is a coupling with a healthy system, healthy system S. Over time, it will be brought low by the disease. It will also get infected, and once it's infected, it can spread it further, right? And so on and so forth. So this is the way I imagine this happening. And I think this analogy is pretty well. It expresses the intuitive understanding pretty well, I think. And in our analysis we did on the previous lectures, we we really focused on this bit here, the process of infecting, let's say, how the healthy system grabbed by this buff turns into piece of a buff, right? Turns into thermal equilibrium as well. Uh, Now this spreading, whether this system S really gets this ability to spread the disease of thermalization further on, let's put a pin into it. Okay, so we put pin into it. Put a pin into it. Okay, because strictly speaking, we haven't considered this yet, this part. We believe, I believe, and I think most physicists would believe that this is what will happen. This is what the essence of thermalization is. But so far, we just investigated this, this first transmission of the disease, let's say. I'm saying put a pin into it because we will get to that. Okay, we will think about it on the next lecture. But let's stay here. Let's stay with this our maybe overblown analogy with spreading, spreading zombie virus. Because if it is like a disease, it spreads. There are symptoms. The state turns into thermal state. But what is there is a it spreads through contact, right? Through interaction, right? There is this thing. There are symptoms of the disease, yeah. But what is this pathogen? You have the disease. Disease produces symptoms. There is a channel for vector for transmission. But what is transmit? But in the biological diseases, or even maybe computer diseases, you know that this what is transmitted through the interaction is a pathogen, like a virus, bacteria, or whatever else. is responsible. So if this analogy with spreading disease is to hold, right, then what is the pathogen in this scenario, right? And this is like a maybe a little bit silly, but I find quite a fun bit of exercise, intellectual exercise to have a swing at this problem. What is the pathogen in this thermalization disease? So we have a couple of options here, right? And we have the maybe the state, the thermal state, the equilibrium state is somehow the thing responsible for the disease. But like I said, I think of the state more of a symptom of the disease, not the cause of it. This is what the disease leads to. The pathogen leads to the thermal equilibrium state, but it's not itself a pathogen. It might facilitate a further spread. Yeah, that's true. But this is not itself a pathogen. And why do I say that? Well, I think that the main thing is that the transmission of the disease, okay, the way the dynamics work of thermalization, right, is governed, at least in this model we investigated, is governed by this generator, Davis generator, okay? And of course, you look at this Davis generator, you have a bunch of things flying around here, but it's not like the initial state of the system is the thing is like explicitly present in this generator, right? In these things that controls the dynamics, controls the spread of the disease. You can say, okay, it is buried here somewhere, right? It's in a transition rate in this lamp shift, because we look into it, down into it, you see that transition rate is some, half Fourier transform, some complicated transformations of the correlation function for environment, and this correlation function it has the initial state in it, encoded in it. But but it's buried very deeply, right? If you could make this transition rate to have the same form, but with some by other means, let's say, maybe this correlation function doesn't really have this initial state as this, but it's still there's some different combinations of factors in this under this trace. But in the end, when you do all the Fourier transforms and stuff like that, you will get with rate that is just right for the thermalization to complete. You would not be the wiser, right? So because the initial state, it does bring in the information about temperature for sure, which is like important ingredient for establishing this asymptotic limit, right? Because the state, I mean, the system has to know where it goes, right? What is the temperature is supposed to reach when it's in equilibrium, right? And this temperature originates, if you break everything down into constituent parts, it originates from this P beta here, but P beta gets processed so much before it gets in this information gets to system S, that it's not clear that this is like a root cause of what's happening. You could imagine that maybe you could like replace it with something else, some other conditions, some other circumstances, so you will get the same result in the end because it's so post-processed, right? So no, I don't think the thermal state of the bath is the pathogen we are talking about here. It's just too removed from the very mechanics, very dynamics of the whole process. So if it's not the state, uh, then what other options we have? Where if we look at the generator of dynamics, we have a couple of things here. For example, we have a coupling operator, right? So we have a coupling of this form, S on the side of the system, F on the side of the environment. And what actually enters the dynamics is these decompositions, frequency decompositions mm, of our coupling operator. No, sorry, it's not like that. Sum over AB, delta omega AB, omega A, and we have here some matrix elements of this coupling. But I would still say this is not it. Because when we looked at we did a lot of math. We investigated how the generator decomposes, how it works, and so on. And of course, a lot of stuff was, I mean, those matrix elements of the coupling for sure came into play, right? For example, they surely contribute quite directly to the magnitude of eigenvalues of our generator, which in turn control how fast the whole process is going, right? Uh, and for example, to be sure to get a full dephasing, so to get the full thermalization, full infection, let's say, full infect the system S with thermalization. Well, I told you I didn't show you in detail, but believe me, and you can check the notes if you want to see for yourself. But we had to, for example, assume that um, the coupling operator, oh, right, this condition, that the all energy levels are connected for this coupling. So surely it has impact on the whole process, on the whole dynamics of the process. But I would say that it's not like, let's say if you violated this condition, you would somehow like stop the thermalization to some extent. You would make it not perfect, like not it would be not full thermalization, but almost there because you could open up, you would open the possibility for some pieces of diagonal elements of the density of the initial state to remain there and evolve, oscillate or something like that. So I would say that maybe the coupling it's not the pathogen, it's not the thing that causes the system to thermalize, but it is surely a part of like the how system is resistant or susceptible to the infection, to the pathogen. Okay, uh, so it's like if your system does not is system is very resistant, so it's like this coupling is very sparse. A lot of energy levels are not connected. Then it will resist the infection, right? The density matrix will remain, let's say, longer or maybe indefinitely not fully thermalized. Right? There will be some pieces of the system that are immune or maybe resistant to the disease. But it's not the thing that causes the disease, causes the thermalization. And also, the condition like this, you can, it kind of control how the dynamics looks, how resistant the system is, how long it can fend off the disease. But it also like not very fundamental, probably this kind of condition, because likely it's just an artifact of the fact that we are using a second order approximation in our for our dynamical map, right? So is the this is the part of the Born Markov approximation, right? And it is a second order, so naturally, second order involves only like let's say direct connections between energy levels. So if some of them are some of them are zero, some energy levels are not connected like that. This, according to the second order approximation, there would be no communication, let's say, no pathway for the disease to spread. But if you go to higher order corrections, I imagine that you would get some other options. So say higher order, higher order corrections. Higher order corrections might open, stuff like A, C, S, C, B. Let's say something like this, right? So if A to B is not possible because SAB is zero, then the higher order correction would allow you for indirect pathways, let's say. So this would, so you go, this is not allowed, uh, but maybe this is allowed. You go to C and from C to B, right? So this is knocked out, but this is not, and only higher order of the perturbation theory would enable this kind of pathway. So what I'm saying here that as the coupling is important in the sense that it takes part in the mechanics of the dynamics of the whole infection process, but this is only like let's say, this only allows for the pathogen to go into the system and infect it. So if it's those pathways are closed off, it's a lot of the system is resistant. If they are open, it just overwhelms the system much faster, and the thermalization is completed fully, right? And this is like how it affects the whole dynamics. It's probably the way you describe it is somehow contingent on what kind of perturbation theory you are using, what kind of approximations are valid here, and then probably you can show that if you like do more precise calculations, this the resistance caused by the shape of the coupling is probably less effective than you would imagine in the first place, based on the analysis we did so far. So sorry for rambling about this, but so this long story short is that it's not the state, it's not the thermal state, that's not the pathogen, it's more of a symptom. It's not the coupling, the exact form of coupling. This is just a pathway for the pathogen to go through. Uh, so what's left? What could be play the role of this pathogen? Well, the last element I think that's present here is the transition rate. Okay, so if this S was the side of the system, the coupling from the side of the system, the transition rate is like somehow captures the buff part of the coupling, right? Because it's like it's a Fourier transform of the correlation function of the buff side, environment side of coupling, right? Uh, so again, you could make some similar arguments as with S that if this is like it encapsulates mm, the coupling, but from the other side of the infection, this is maybe should be thought of as a mm, transmission path for the pathogen, not the pathogen itself, right? However, uh, the transition rate has more to it than just than what just the operator S has. There's more stuff going on here. I mean, obviously, right? It's a more complicated expression, and m- more specifically, it's not like the W for any specific omega is super important. What we looking through our analysis of this whole process of thermalization, especially I mean, mainly on the previous lecture, where we like, looked at some H theorem and stuff like that. We are making sure that this thermalization, this process of thermalization is like inevitable, and that, the thermal state is like the attractor of everything. The key part of, all those calculations, the theorems and proofs, was not like a specific value of W. No, we just had to make sure that W of some omegas is not zero. So it was like similar to, the similar as some conditions of S. But what really was important was the relations between different W's, specifically the detailed balance, right? Detailed balance, right? The value of each W, of each individual transition rate for any specific frequency is one thing, but what was super important was that this ratio, right? Omega. Okay. Because, this is what enabled, the block, this is what enabled mm, the H theorem. This is what enabled us to establishing that mm, because of the symmetry brought about by detailed balance, we could show that the thermal equilibrium for system S is the like steady state solution, right? And then we brought it to show that through H theorem that it's not only steady state solution but also an attractor, and and many other places. And so this ratio, right? This ratio, this property seems to be like important, and it also, as it happens, this is also what like explicitly brings in the dependence on information about beta, about the temperature of the bath, right? And the target temperature for the system to get to eventually. Uh, so detailed balance was like, so there is something about it. And where the detailed balance comes from actually, right? So, we have our transition rate, which I wrote down the formula here, half of the Fourier transform, blah, 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 blah. But what was pretty crucial about, I mean, the detailed balance came not just from this formula, but the fact that the transition rate can be subjected to fluctuation dissipation theorem. So what I mean that we showed it some couple of lectures ago that fluctuation dissipation theorem allowed us to rewrite this admittedly complicated admittedly complicated expression into more more palpable form, spec E beta omega plus 1, right? This is what fluctuation dissipation theorem gave us. So we knew the transition rate is a spectral density of the coupling, of the environmental coupling, right? So this correlation, Fourier transform, all that stuff, just basically you can pack it into the spectral density, which you can think of, I guess, as like it quantifies how strong the coupling is on the side of the buff. And this strength comes in when you need to determine, eigenvalues of the generators, which in turn, control how fast everything happens, right? But the real boom, the real contribution from fluctuation dissipation theorem is this thermal factor here, right? This thing is just, how big, if it's big, everything will go faster and stuff like that. But the shape of this spectral densities is largely immaterial, right? It's just, It just tells you how things will, before it gets to the thermal equilibrium, which pieces of the density matrix along the way will get, dumped faster and stuff like that. But the ratio, the detailed balance, comes from this thermal factor. And again, this is the place where the explicit information about temperature comes in, right? There is no, it's not like the density matrix comes in and exposes the beta in the exponent here. It's nothing like that. Where it comes in is by, setting up the specific relation between like a real part and imaginary part of the correlation function of the coupling, which is what fluctuation dissipation tells us. This is what allows us to get this thermal factor in front, and this is what gives us the detailed balance. The detailed balance gives us all the rest of the stuff. So what I'm getting here to is what I want to say is I think that the pathogen in our scenario is the fluctuation dissipation theorem, is the concept of fluctuation dissipation theorem. Or maybe, this depends how you want to look at it, but rather than fluctuation dissipation theorem, maybe a concept of detailed balance is what is the pathogen, what is this information that that steers the dynamics of this system S towards the thermal equilibrium. This is what the spreading of the thermalization is all about. This is what enables it. And you might object to this. It's like, okay, I mean, pathogen. Pathogen is a thing, right? It's a virus or bacteria. How come a concept like fluctuation dissipation theorem or concept like detailed balance can be thought of as a pathogen? But if you think about it for a bit, what is a virus? Virus is just some lipid or protein shell enclosing a DNA, right? And the shell and all the other circumstances of the transmission of the disease are just there to facilitate uh, getting this DNA or RNA or whatever from enclosed in the virus straight to the host cell, right, into a nucleus of the cell to do the actual infecting. So uh, everything except for if you look at it like that, you reduce it to concept like this, everything except for the DNA in the virus is just a part of the transmission part of the transmission process, getting into the cell. But before that, you also have, I don't know, some areas, droplets or bodily fluids and stuff like that. Everything that's just a part of this transmission process that gets the virus from infected host to the cells of the victim, right? That it's supposed to infect. But all this is just a part of a transmission of this DNA strand into the host cell. But then, but you can reduce it even more. It's like, well, what is DNA, right? It's also a bunch of chemicals there, right? A bunch of I don't know the proper nomenclature, but ultimately DNA is just a physical carrier for the information, right? Encoded in it. And this, so if you do it like that, if you look at it like this, then even this transmitting DNA into the host cell uh, through the molecule of DNA, still the molecule of DNA is just a vehicle for inputting the information from the virus into the machinery of the host of the victim, right? Of the victim cell. right? And this information, this is what defines the pathogen as a pathogen, right? Because this information is what allows it to hijack the cells to manufacture more copies of itself, right? Of the virus, of the DNA, of the information inside. And all this information, how to copy itself, but also copy itself with all the bits and bobs that allow it to transmit itself further, right? So if you do it like, if you look at it like that, admittedly, maybe it's a little bit silly, but what makes a pathogen is, all the biological machinery along the way is it is of course important for the dynamics of the transmission, but what really essence of the pathogen is this information encoded in the DNA, right? So it's a concept. In other words, what I want to say is a concept. So I think the fluctuation dissipation theorem or detail balance is like this information encoded in the DNA of the virus or viral bacteria or whatever else. And it's not like super silly analogy because this is look the fluctuation dissipation theorem gives you tells you that the transition rate has this thermal factor here. This thermal factor implies detailed balance. Detailed balance implies all the how the generator looks like, the shape of it, uh, so that it molds the shape of the generator so that the thermal state with the temperature given by the that came from here with temperature beta is the steady state solution, also an attractor, right? And now uh, once you do this, so you pass on all those instructions, you get your dynamics, you get to thermal equilibrium. But then, look, thermal equilibrium, being in the state of thermal equilibrium is also the sufficient condition for having fluctuation dissipation theorem, right? So if system S goes into thermal equilibrium, well, this is the reason for that. Let's say if this was the disease, the reason for that is so that it can now reproduce fluctuation dissipation theorem for its own observables, so that the next guy comes in and start interacting, and the transition rate that this S prime sees will also satisfy fluctuation dissipation theorem because the setup was that the system S is in thermal equilibrium, right, which enables the fluctuation dissipation theorem, which enables detailed balance, and so on and so forth. So this is my pitch for you, right? So I think that the thermalization, there is some analogy, maybe it's even quite good analogy between infectious disease and thermalization, the process of thermalization. And like any disease, it has symptoms, it has, some mechanics of transmission, but there is also a pathogen, right? And my pitch to you is that the pathogen in case of this thermalization disease is either detailed balance, the concept of detailed balance or fluctuation dissipation theorem, which are uh, or maybe you can even find something like more high level that like implies those two guys or something like that. But this is this concept of this balancing, that the fluctuation and dissipations are in very specific relation to each other. And all the other stuff comes from that, and the way that this balance works is such that such that it reproduces itself through this process of thermalization, so that detailed balance can be achieved further down the line, and the thermalization can spread. So it's like evolutionary pressure for if you want something that could be spreading, it has to be in essence, it has to have all those mm, it has to be able to satisfy those prerequisites for it to, to spread further. So, and this prerequisite, the thing that like suffices for this kind of spread is this idea of detailed balance, let's say, in the system. Okay, so this is like my physical understanding of the process of thermalization. And now, if you want to go even further with this analogy, if you are brave enough, so we could like maybe we identify this pathogen, we have like this transmission broken down into pieces, we have the mechanics understood to some extent, but if it is a disease, there is this patient zero here, okay? The initial bath with initial bath in thermal equilibrium so that it has this detailed balance for its observables, right? But if it, where this, where did this patient zero came from, right? What's its origin? Where the pathogen came from in the first place, right? What is the origin of the disease? And this is an interesting problem, and it's not unsolved problem. I'd like to say, and it's a subject of quite intense research at the moment and in the past. And I I won't be talking about it here, mainly because I don't really know much about it. I don't feel like competent to talk about it. But if you are interested in this, where the patient zero came from, I my recommendation would be to look up a thing that's called eigenstate eigenstate thermalization hypothesis. It is a very interesting idea. So this is a hypothesis. So this is like one of the attempts at like explaining that how if you have because if you have open system that can couple to already diseased baths, the mechanism for thermalization, we just talk about it for 5 hours or something. There's a lot of stuff you can see in it. But to answer the question where it begins, where the patient zero comes from, well, then it's like you turn this into a different problem. That okay, let's say you have a closed system, so there is no communication with any. There's no possibility for communication with any other already infected baths. You just have a closed system. Is there a way of looking at it so that you could argue that it becomes, or its natural state of being is the thermal equilibrium or something like that. And there are some brave, interesting considerations about that, and like eigenstate thermalization hypothesis is like one of the approaches that people are investigating and have high hopes for. So if you are interested in this particular thing, look up eigenstate thermalization hypothesis and start reading and go from there. But we won't be getting into more details about this. And now, this is like essentially closes all the stuff I wanted to talk about regarding thermalization. But there is still this one, this one put a pin into it, right? Because I talk about thermalization and I said, okay, there is a spreading of the disease that, BAF infects the system S, and so that it makes it a vector for further spread of thermalization. strictly speaking, we haven't touched that. We don't know that. We haven't seen this. This is I'm just like I would love to. I mean, we kind of know intuitively and from other branches of physics that this is how it should work. But can we actually describe this? The fact that infected system becomes a vector for further spread of the infection further down the line. Okay, can we use our methods of open system theory to actually describe this stuff? And as it will turn out, will be topic of our next lecture. Uh, we have to develop those methods further to actually capture this kind of process to fully describe this spreading of thermalization. For example, not only that, but that's one of the more fun cases to which we can apply this next step in our formulation of open system theory. But that's a topic for next lecture. For now, we can finish on what we have here.